discussing a paper about hand coordination and also discussing a video by Andrej Karpathy about tokenization. And I think they're related because in the paper, the authors are basically discussing what representation to use when solving the problem of hand-object coordination. And in the Karpathy video, Andrej, as usual, brings up really interesting points when it comes to transformer technology. He talks about tokenization, which is kind of a more technical way to say the same thing, which is, okay, how should we even represent the data? If you think about, if you step back for a second and you look at transformer architecture, and you just sort of try to explain that to your mother or your non-technical wife or whatever, you will say, look, what's happening here is that we take reality as it is, whether it's text or whether it's multimodal, whether it's pictures, videos, sounds, and we compress it. And that compression is, on the one hand, useful in terms of storage and things like that. We can store reality in a much more compressed way. But more importantly, also, we're able to read from that compression and extract information and use algorithms to read, in the case of transformers, what you would read as tokens, and use those tokens to infer things. And that's what's called inference. And that's how, when you prompt, a text in GPT, you get an answer. And hopefully in the future, a robot will be able to use transformer architecture to do inference on reality and walk around and do stuff. So that's kind of what the problem set is here. The paper is, again, these are two unrelated things, but they're kind of connected through this issue of tokenization, or more generally, representation. So what I want to talk about here is sort of my conclusion, which is, I recently posted a question on X, which is multimodal transformer architecture a good solution for physical robots? And the answer is yes, it is definitely a good solution. But the question is not whether it's transformer or not. The question is, how do we represent reality? What representation do we use? Or what tokenization do we use? So that's why I think the Karpathy video is very useful, and this paper are very useful. These are two again, unrelated projects that, in my opinion, are connected by this arch of representation. This is not even on podcast. It's February 26, 2024. This is Krim Zelko. For today, the fund is up 3.8%. The market is down 38 basis points. For the year, we are down 10.7%. The market is up 6.3%. We're underperforming by 17%. There's two projects I want to discuss. One is a paper on Archive, and one is a video by Andrej Karpathy. The paper on Archive, I'm going to put the names in the show notes, so I don't want to spend time here with details. So the paper describes hand-object orientation and how to solve this problem. So you have a robot hand, and the robot wants to grasp something, and you want to solve this problem in a generalizable way so that the robot tomorrow can see things and automatically grasp them without having any kind of explicit program or anything like that. So what we're talking about here is what sort of in more layman's terms is considered end-to-end learning. So we don't want to hard code anything. We don't want to explicitly tell the robot that a glass is glass and it should be careful in not breaking it. None of that stuff. It should be simply go and grab that glass and put it in the dishwasher. And how can we achieve that? And the authors are using a certain representation technology. In a nutshell, what they're trying to do is they're saying, okay, why don't we represent this interaction in a certain way such that the surface of the robot hand is encoded, the distance between the robot hand and the object is encoded in a certain way, and the object surface is encoded, and then there's some sort of time elapse between the object and the hand, and we encode all of these things or maybe tokenize it in a smart way so we can use an algorithm, whether it's reinforcement learning, whether it's masked autoencoder or something like that, to then train the robot to grasp the object. And this leads me to the second project, which is a video by Andrej Karpathy, highly recommended. It's about tokenization. Now let me talk a little bit about the video and then get back to the hand-object orientation problem. The video in general is introducing the idea of tokenization, which in other words is how do we actually represent a body of, in the case of large language models, how do we represent a body of text in a way so an algorithm can learn from it? And the answer is we tokenize it. So tokenization can happen on a byte per byte level. It can happen per word. It can happen per sentence. That's part of the question. There's a design space, and Karpathy introduces some papers in that context. We can actually spend time thinking about what's the best way to tokenize a text. In the Karpathy video, he uses a very simple tokenizer where he uses bigrams, so character pairs, and he tokenizes them. So I am going for a walk, I space is a token, AM is a token, space G is a token, OI is a token, and G is a token, so on and so forth. He then looks at a compression algorithm which says, okay, once I tokenized all the bigrams, how many of those are very often? Let's say in the case, for example, we could have space, E space happens very often because most words end with E and then there's a space. So E and space is a bigram that happens very often. So we can tokenize that and call E space, let's say token 256. And then from now on, every time we have E space, instead of saying, E space is just token 256. So we can start compressing the knowledge. And there is a certain optimal way of we can keep compressing and compressing, or we can not compress. That's part of the design space, which then goes to the algorithm where we have what's called the context length, and where we have to take that into account. If we have a very granular representation of reality, so a lot of tokens for a lot of different situations, then we will have a problem with the context length. In other words, we need a very long context length to really do intelligent inference from this model. If we compress more, we can have a shorter context length and still make inference. However, a lot of compression, by definition, loses information. So there is this canonical question in AI today. What kind of tokenization algorithm do we use? So I think this is very interesting because this is sort of a subfield, but it's central in a sense that if we tokenize properly, we can solve a lot of problems that the architecture and the algorithms might be able to solve, but it's a lot more difficult. So in other words, this is, if we represent reality in an efficient way, then the training and inference can be done much, much easier. So to paraphrase Elon Musk from the last earnings call when he said, the better we train our model, the better the inference is, which is something that we highlighted, and we focused on Dojo and the H200 NVIDIA technology, and this idea that the better we train things, the less energy, the less mistakes, the less headaches, quite frankly, we're encountering, and vice versa. If we have a suboptimal representation of reality, if we don't train well, of course we have a headache. Now, training well is a nice thing to do, but what exactly does that mean? And that's, I think, the gist of Karpathy's video, is that a well-trained model starts with a well-tokenized model. And tokenization is a fancy word for how do we represent reality? What do we use? And now let me arch back to the first paper that I discussed in this episode, which is the idea of hand-object coordination, right? And we can extrapolate this now to, let's say, self-driving. Any kind of robot problem, we can ask ourselves the same question. Okay, first, is transformer technology a good architecture choice for robotics in the real world? The answer is yes. However, the question is really, what representation do we use, or what tokenization? Let's say, how do we tokenize the hand of a robot and the space between the hand and the object itself, and how do we tokenize the actual the action when the hand goes and grasps the object? Those are massive questions. I think this is an open design space, and I certainly don't have answers here. I'm not a researcher. I am an investor, and the reason we do this here at Orange Capital Partners is because we want to understand the intricacies of the technology to be able to extrapolate to what kind of investment we should then we should conduct. And I think what this tells us here is, number one, that a lot of architecture choices are sort of, if you want, a big picture choices, but in under the hood, the subtle differences in tokenization can make a very big difference. whether that is a good or a bad thing for a particular stock, that's a whole different question. But I think it's good to understand the direction where this is going, because it answers a few big questions. One is, multimodal transformers are a possibility, but we need to spend time on tokenization, because that's where, in particular, when we talk multimodal architectures, that's where things like training time, things like inference time, power consumption per inference, things along those lines, that's where they come into play. If we have a good representation, again, I think the summary of this episode is really that AI is about representation, and representation is called tokenization, and that's a key point. That's why Karpathy made this video, and he highlights some of the general issues. For example, why are certain models not very good with our arithmetic? Well, it's because numbers are tokenized in a suboptimal way, and if numbers are not tokenized consistently, then you could have a very simple arithmetic question, such as 5,600 plus 7,800, and those numbers could be tokenized by number, or they could be tokenized by pair of number, or they could be tokenized by space number, and then when you add them up, it becomes sort of a confusing situation. The same applies to things like programs, and a lot of research has been done in that front. In particular, of course, OpenAI in context with Microsoft, because they wanted to launch the Copilot, which is a big money-making product for Microsoft. So, just as a sort of tangent here, the problem in programming languages and tokenization and large language model is, how do we tokenize, for example, indentions, spaces, which are crucial in the programming languages. A space or an indention is information. It's not just some aesthetic thing. And if you don't have a precise representation of that, then the model will learn randomly how to, let's say, indent a certain a line of code, and then of course the whole code can fall apart. So again, to summarize, two interesting projects. One is the problem of hand-object coordination, which in the paper is being tackled by finding efficient representations of the hand, the space between the hand and the object, and then we have, on the other hand, a video by Andrej Karpathy about tokenization, which is another way to say it's about how to represent. In the case of Karpathy's video, it's text, but we can easily extrapolate that to multimodal. How to represent the body that we're trying to learn on, and then what kind of architecture, what kind of algorithm do we use in terms of representation. I think lastly, what I want to say is, there is this beautiful allegory, if you will, or connection between biology and AI. In biology, we have the doctrine of biology, which is DNA, RNA, protein, right? And in AI, we have data, we have architecture, model, and algorithm, and those things are not linear. They are, if you will, or to use the language of AI, they are forward and back there's forward propagation and back propagation. They're interconnected. In other words, we have the data. Now, how do we represent the data determines what kind of model we can use, or what kind of algorithm we should be using, even what kind of architecture we should be using. Maybe we can sort of consent on a transformer idea. The idea of the transformer is pretty powerful in terms of self-attention and things along those lines. But now the question is, okay, what kind of representation do we use when we train those models? And the more efficient the representation is, the better we can then do inference on. And this is really the key. This is the gist of, I would say, the next 1 or 2 years of AI, and also the door that will open real-world AI, physical robots, self-driving cars to the public. Thank you.